Okay, so welcome back to this next video in which we are discussing the alternative pathway of complement activation. Okay, right, so we had got to the point where we were talking about what C5b is going to do. So C5b is in the interstitial fluid at the moment, and it's going to assemble with the complement protein C6. Then once you've got this C5b-C6 complex, another complement protein is going to add on, which is the complement protein C7. Okay, and we'll have C7 in blue here. Okay, so this is C7. Ooh, horrible black smudge there, never mind. There's C7. So what you're going to get is this complex involving all three of these now. So you'll have C7 on the end here, then C6 in the middle, and then C5b right at the end. Okay, so let's highlight them all in, so that we know which ones are which. So that I think the colour helps. It means that you know which one's which without having to actually look into much detail. Okay, so it simplifies everything, colour. Okay, so here's C6 in green. And finally we have C7 here in blue. Okay, right. And then finally another one is going to come and add on. However, this is an important one now. C8 is going to come and bind on, but when C8 binds, the whole thing is now going to get translocated. It's going to move into the membrane of the microbe. Now, I have previously been denoting the membrane just as a single line here. Okay? We're now going to have to expand that view. Okay? So we're going to have to acknowledge that the membrane is not just a line. In fact, it's two layers. Okay, two layers of phospholipids. So it's a phospholipid bilayer. So here is the membrane of the microbe drawn again. Okay, now this could be the phospholipid bilayer of a bacterial cell. It could be the phospholipid bilayer of a viral envelope. It could be the cell membrane of a fungal cell. Whichever microbe you are talking about, they will have phospholipid bilayers. Okay, so this side is what I mean by, well, what's going to represent the outer leaflet of phospholipid bilayers. The outer leaflet of the phospholipid bilayer, and it's the layer of phospholipids which is facing the outside world, basically. Whereas this is the inner leaflet, and this is the layer facing, in the case of the bacterial cell or the fungal cell, it's facing the cytoplasm. In the case of the virus, it's facing the nucleocapsid within. Okay, so what's going to happen is in this phospholipid bilayer, you are going to get this entire big complex implanting in. So this is a complex of C5b with C6, C7, and C8. Okay, so here is C5b at the top here. Then underneath you have C6, then C7, and then right at the base you have C8. Okay, so you've brought in C8, and when you bring in C8, the whole thing implants into the phospholipid bilayer. So this is the final complement protein C8. Well, it's not the final one, we're going to have C9 as well, but it's the penultimate one. So here's C8, okay, in turquoise. So C8 is in turquoise, then C7 is in blue here at the base. C6 is above that in green, and C5b is above that in red. Okay, so what's the final step then now? Well, basically, you're going to bring in C9 proteins, but you're not just going to bring in one C9 protein. You're going to bring in a whole bunch of them. So here is a C9 protein. Okay, and we'll have this C9 protein in vivid purple. And basically, you are going to assemble an entire ring of C9 proteins. Let me draw this. So you're going to get a whole ring of the things, like so, making a cylindrical pore through the membrane. Okay, so here's the hole, and then you've got all of these proteins. So here's 1, 2, 3, and how many do you bring in? Well, generally it's between 10 and 16, but it can go as high as 19. So we'll aim to put 14 on there. Okay, so 1, 2, 3, 4, 5, 6, oh dear, it's not looking good, 7, 8, 9, 10, 11, 12, 13, there you go, that's enough. Okay, so 13 we've got. Okay, so it varies, it's not a fixed number that's going to assemble, but we've got these separate C9 proteins all combining together to make this cylindrical pore through the phospholipid bilayer of the through the phospholipid bilayer of the microbe membrane, whether it's a virus or a bacterial cell. Okay, so just to make this crystal clear, one of these subunits here is a single C9 protein. Okay, so this is this up here. Okay, and this complex here of multiple C9s is what's known as the membrane attack complex, or the MAC for short. Okay, now what does the membrane attack complex cause? Well, it's going to cause osmotic lysis of the microbe, basically. So let me explain why. So basically, the inner compartment that is contained within the phospholipid bilayer, whether this is the cytoplasm of the cell or whether it's the nuclear capsid of the virus. So here is our membrane that has an inner compartment here. So I'll say the inner compartment of the microbe, that's how we can cover them all. And then it has the outer compartment here. Basically, in all cases, whatever type of microbe we're talking about, the inner compartment has a much higher solute concentration than the outer compartment. There's a fancy word for this. We say that the osmolarity, okay, which means how much solute you have dissolved in a fluid. That's the osmolarity of a fluid. It's not about any particular solute. It's not like sodium ions or potassium ions. It's all of them together. So you add up absolutely every single thing that's dissolved in the fluid. That's the osmolarity. So it's basically like concentration, but you're not saying deliberately which one you're talking about. We're not talking about concentration of sodium ions or concentration of potassium ions. We're talking about concentration of everything. So it will have within it the sodium ions and the potassium ions, but it will have everything. Okay, so that's what's meant by osmolarity. Okay, we say that the osmolarity of the inner compartment is much higher than the osmolarity of the outer compartment, which just means that the amount of solute that is dissolved in this inner compartment is much greater than the concentration of solute in the outer compartment. Okay, right. So, when you have a osmolarity difference, basically it leads to osmosis, which is the movement of water due to an osmolarity gradient. Okay, also called an osmotic gradient. So water will tend to move from the area of low solute concentration to the area of high solute concentration, and this is what's known as osmosis. Okay, right. So, another piece of terminology that's used is water potential. You will often hear people refer to water potential, especially in more modern texts. Okay, so water potential is the exact opposite of osmolarity. It means how much potential the water has to dissolve things. So if you've got a very high solute concentration, then the water potential is low because the potential of the water now to dissolve more is very low because it's already got absolutely loads dissolved in it. Whereas if you've got hardly anything dissolved in you, your water potential will be much higher because your potential to dissolve more solvent is good. Okay, so we say that the outer compartment has a high water potential and the inner compartment has a low water potential, and osmosis that occurs from the area of high water potential to the area of low water potential. Okay, so don't let those two confuse you. Okay, so water will move from the outer compartment to the inner compartment via osmosis. Well, it would like to anyway. However, the problem is, for the microbe, that if this happens, what's going to happen is you're going to get more and more water in the inner compartment, and this is going to cause the volume of the inner compartment to swell, and that will cause the bursting of the membrane, basically, which is not good. Okay, so we don't want water to come in. Now, luckily for the cell, the phospholipid bilayer is very good at stopping water from coming through, because it has this hydrophobic core at the center here, where you've just got loads of hydrophobic molecules which don't interact very thermodynamically favorably with water. So water struggles to cross this phospholipid bilayer. However, when you stick a great big pore, like the membrane attack complex, in this phospholipid bilayer, the water can skedaddle through this pore and hence go into the inner compartment. So once you put these membrane attack complexes in all over the microbe membrane, you're going to get water moving into the inner compartment via osmosis, and that's going to lead to the cell swelling, and that's going to lead to the bursting of the cell, known as osmotic lysis. Okay, so that's the final way that the alternative complement pathway can can contribute to killing the microbes. Okay, so to summarize then, the alternative pathway is initiated by a spontaneous breakdown of C3 into C3A and C3B, which occurs all the time. Now, the C3B might just happen to bind to a glycoprotein on the surface of a microbe, and the microbes do not have protection molecules such as cyanic acid or C3b inhibitors to stop the C3b from setting up a positive feedback loop on the surface of the microbe. So what will happen is C3b will bind to the B protein, which will then be activated by factor D, which will break B down into BB and BA, and the BB will remain bound to the C3b. Okay, properdin will then bind to the C3b-BB complex to stabilize it, and then what will happen is that the C3b and BB complex will then set up a C3 convertase, and it will start converting C3 into C3a and C3b. So you started off with a very rare reaction of C3 breaking down into C3a and C3b, whereas now you've got a very, very fast reaction which is chucking C3b out at the cell. The C3b will end up binding to glycoproteins on the surface of the cell, and they too will bind to B protein and set up these C3 convertases. So you get a positive feedback where the microbe just ends up covered in C3b. The phagocytes, neutrophils and macrophages then have a receptor for C3b on their surface, and this will lead to them phagocytosing the phagocytosing the microbe. Okay, then the other contribution is that you're also chucking out this amylotoxin C3a, which is going to lead to degranulation of mast cells and type 1 activation of endothelial cells. So you're going to have a positive feedback loop of the inflammatory response. Okay. In addition, what can happen is some of the C3b can bind to the C3b-BB complexes here to form this C3b-BB-3b complex, which will then act as a C5 convertase, which will break C5 down into C5b and C5a. C5a is then another amylotoxin and is going to lead to positive feedback of the inflammatory response. Okay, C5b will then assemble with C6, C7 and C8 and implant itself into the phospholipid bilayer of the microbe. It will then recruit many C9s to form a membrane attack complex, which will allow water to move into the inner compartment of the microbe, causing osmotic lysis of that microbe. So overall, this is part of the innate immune system, which will be initiated against a vast array of very different microbes, which will help to attack invading cells.